Next, let's talk about the mean value theorem. We'll talk about what it is, its physical interpretation, increasing and decreasing functions, and some other consequences. The mean value theorem for derivatives states that if y is equal to f of x, or if y equals f of x is continuous, there's that word again, continuous, at every point of a closed interval a to b, and differentiable at every point of its interior AB, then there is at least one point C in AB at which the derivative at that point is equal to f of b minus f of a over b minus a. Now that was pretty wordy, but it's not all that difficult to understand. When I first introduced you to the concept of derivatives, I oftentimes use the comparison between average rates of change and instantaneous rates of change. If we look at this graph here on the bottom right, we can see this black line is an average rate of change. Average rate of change. We have rise over run, and we can get an average of how much our function has changed between point A and B. Now, what the mean value theorem says is that, yes, we have a bunch of different tangent lines over that interval. However, if from the interval A to B, our function is continuous, meaning it doesn't have any discontinuities like holes or asymptotes, and is differentiable at every point between A and B, then at some point our derivative, one of our tangent lines, like this pink one over here, is going to have the same exact slope value as the average over that area. That's why this is called the mean value theorem. It basically connects average rate of change over an interval, as we can see over here, with derivatives. Now, obviously, if you take a derivative right here, that's going to have a way different slope than this line. It's almost 90 degrees to it. But at least one point over this interval, one derivative has to have the same slope, the same value as the average rate of change over that same interval. Sometimes it can be two. It doesn't have to just be one. It can be multiple different ones. But to kind of think about it in a real-life application, again, if you were driving a car down the highway at 120 kilometers an hour, and then you were stuck in traffic for half of that time where you weren't moving at all, that would have the same average speed as if you were constantly driving at 60 kilometers per hour. The average would be the same, but the driving would be really different. What the mean value theorem states is that if you had a super erratic trip where you were constantly speeding up and slowing down, but your average speed was, let's say, 60 kilometers per hour, then at some point, no matter how quickly you were going at one point or another, at some point your speed will be equal to the average speed. So once again, one of these tangent lines is going to have the same slope as the average rate of change lines, the secant line. This is just a very wordy way of saying all of that, but it is important to remember. And this is basically the physical interpretation of that. This is just what we talked about before, except summarized a little bit more nicely. If we think about the difference quotient, f of b minus f of a over b minus a, which is your basic average rate of change equation, as the average change in f over a to b, and f prime as an instantaneous change, then the mean value theorem says that the instantaneous change at some interior point must equal the average change over the entire interval. And here's a great example, very similar to what I was just talking about with the car. If a car accelerating from zero, takes 8 seconds to go 352 feet. Its average velocity for the 8-second interval is 44 feet per second, or 30 miles per hour. And again, that's this interval right here. Draw that as carefully as I can. The average rate, its average speed over that period of time is 44 feet per second, aka 30 miles per hour. At some point during the acceleration, the theorem says that the speedometer must read exactly 30 miles per hour. So again, at some points here it might be going faster than 30, at some points it might be going slower, but at some point, if the average is 30 miles per hour here, there has to be at least one tangent line here that has a slope that's the same. At this point, the car speed will be 30 miles per hour, matching the average rate of change. Let's skip ahead to the definition of increasing functions and decreasing functions. We have here, let f be a function defined on an interval I, and let x1 and x2 be any 2 points in I. So number one, if function f increases on I, if x1 is less than x2, and the y value, f of x1, is less than f of x2. And conversely, the function f decreases on I if x1 is less than x2, but f of x1 is greater than f of x2. As we can see with this parabola here on the bottom, this part is decreasing and this part is increasing. Very simple. And how does this tie into derivatives? Well, let's look at this corollary number 1 here. Let f be continuous on AB and differentiable on AB. If f prime, meaning the derivative of f, is greater than 0 at each point of AB, then f increases over that interval. So what this is saying is that if our derivative function is greater than 0, has values of that are all greater than 0 over a certain interval, then our original function f is increasing over that interval. And conversely, if the derivative is negative over a certain interval, then that function, the original function f, has to be decreasing over that same interval. As we can see here on the bottom right graph, we have some function here in the black that goes up, down, and then up again. Now let's see how the pink function behaves. The pink function is the derivative, of course. So on this interval, let's look at the roots of it. It's a parabola. The derivative function is a parabola, so let's look at its roots right here and right here. Notice what happens. At these points, the derivative function is equal to 0. And we have a local maximum here and a local minimum right here. So, before this point, on this side over here, the tangent lines of our original function, which is in black, all have a positive slope. So let's draw one like that. That doesn't look very good. But as soon as we get to where the derivative is equal to 0, we have a flat tangent. And then the slope of that tangent line starts going down until it reaches this inflection point right here. And then again, we have another root for our derivative function right there, which means we have another local minimum, we have our first local minimum. And then our derivative function becomes positive again. It's above the x-axis, and the slopes of our tangent lines for our original function here in black have the slope values are positive once more, which is another very handy use for derivatives and calculus in general. You don't need to examine each individual little point. You can just see if the derivative function is positive or negative over an interval, and then you'll know if the original function is increasing or decreasing, and by how much. Here's a second corollary. If f prime of x is equal to 0 at each point of an interval I, then there is a constant c for which f of x is equal to c for all x in I. Basically, this is saying that if the derivative of a function over a certain interval is 0 the entire time, then that function is just a constant at that time. For example, I just plotted f of x equals 2. If you notice on the bottom, we have a derivative graph where the derivative is constantly 0, which makes sense because f of x equals 2 is just a flat line with tangent lines that have a slope of 0 no matter where you are. Our next important little bit of information is that functions with the same derivative differ by a constant. So if f prime of x is equal to g prime of x at each point for an interval I, then there is a constant c such that f of x is equal to g of x plus c for all x in I. So what this is saying is that if two functions have the same derivative function, it doesn't necessarily mean they're positioned in the same place in terms of their y coordinates. And let's take a look at an example of that. Take a look at what happens when I graph x squared. So I have a parabola here that has its vertex at point 0, 0. And take a look at this line here. The derivative function is just 2x. Now, what happens if I do plus 3 or plus 2 so we can see it? Our parabola gets shifted upwards. But notice what happens here with the derivative function. It stays in the same place. Could try x minus 2. It goes down. But still our derivative function is exactly the same. That's because the slopes of these tangent lines don't care where they are on the y-axis. They don't care if the original function is shifted up or down. They just care how much the original function is increasing or decreasing by. And for this reason, when you take a derivative of a constant, it is just equal to 0. It's not really adding anything to the derivative function. It's not any useful information to that. For example, if you're plotting distance versus time for a car, your car might have a different starting point every time, but the speed is still going to be 0. If you're starting from a standstill, it doesn't matter whether you're here or 100 miles away. You're still starting from 0, so it doesn't really matter what your starting point is. Finally, let's take a look at this word right here, antiderivative. A function capital F of x is an antiderivative of the function f of x. If capital F prime of x equals f of x for all x in the domain of f, the process of finding an antiderivative is antidifferentiation. That's a pretty big word salad there, but what this is saying is that if I can take the derivative of a certain function, then I can do the opposite as well. For example, if I have a derivative function, I can anti-differentiate it. I can apply all of the same derivative rules essentially in reverse to get the antiderivative or the original function. For example, if I had a plot of my car's speed versus time, and it was a function, I could find its function. I could anti-differentiate it to figure out what its position is at each point in time. However, there is a caveat there. I don't know what its starting position is because I don't have the constant value that I originally started with. However, to a certain extent, you can do derivatives in reverse and find out other valuable information, which we will cover in great depth later. And that's going to finish up section 4.2, dealing with the mean value theorem.